Okay, so I want to tell you about how a chemical equilibrium works. It's when a reaction is at equilibrium on both sides. To do the experiment, we need to have a experimental setup where we have 7 test tubes with this solution, which was exposed to 7 different sorts of stresses. We also had our standard solution to compare it with the other ones on a macroscopic level, so that we could see if the color changed since it's a qualitative experiment. So why is this reaction useful? It's useful because it reacts very quickly, and also we can use the color as the observations because it's easy to see if there's a favor in reactions or products. Hence, the products are red. So if there's a favor in products, and reactions, we can see if it turns less red or more red. So the chemical equilibrium is when a forward and reverse reaction rate of a reaction, like the one on the right, is the same. It is shown with 2 arrows going in each direction, and this is therefore the equilibrium symbol. The one on top goes right, and the one on the bottom goes left. The symbol is an indication that tells us that the reaction can happen both forward and backwards, depending on different factors such as if we change the temperature or the pressure, or if we have a favor in either reactants or products. The equilibrium constant can be calculated with the equilibrium expression, which we see here. But the result of the equilibrium expression can change, differing from the equilibrium constant, when adding either some reactants or products causing a stress. The ratio between reactants and products will be different from before the stress, which was the purpose of our experiment, disturbing a chemical equilibrium, as seen in our different test tubes 1, 4, 5, and 6. Okay, so in the first test tube we wanted to add iron-free ions to see what kind of change there were, and when we added the reactants, it caused the reaction to use them, which is why it goes down again, and also thiocyanate goes down to make the products on the right, and therefore we get a new equilibrium. So therefore we can conclude that Chatelier's principle applies, because when we add reactants, they go down again to make products. In the fourth experiment, we removed reactants, which resulted in the solution becoming clear. This happened because we added silver nitrate, which resulted in bonding with the thiocyanate, and therefore the concentration of the silver nitrate decreased again. This happened because of when we removed the reactants, the equilibrium counter-reacted this to make a new equilibrium, so therefore it produced more reactants by increasing its rate of reaction in the reverse reaction. And this is also Le Chatelier's principle. In the fifth experiment, we increased the temperature of the solution in the test tube, which made it a little less red, and then it counter-reacted as a result of increasing the temperature, and it increased the rate of reaction for the reversed reaction, because this reaction is endothermic, so therefore it could use the heat to absorb it. So there was a decrease in products and increase in reactants. K was lowered, and since Q follows K, to make it a equilibrium, we get a new K and a new Q, lower Q. In the sixth experiment, we did the complete opposite of before, and therefore we decreased the temperature in a cooling bath, and on the macroscopic level we saw a test tube with a much darker red solution, and therefore we are now able to conclude from the color that the concentration of our products had increased and the reactants had decreased. If we then again compare it to the Chatelet's principle, it says the same, that if we decrease the temperature, it must result in a exothermic reaction, which result in a greater concentration of products, since it goes in a forwards reaction, going towards making products when doing a exothermic reaction. So the chemical expression is with, okay, so there's a difference between K and Q. K can be found when calculating the equilibrium expression for a reaction of two or more molecules. The value of the fraction can change if we add or remove reactants or products. We can remove reactants or products if adding a new molecule, which we did in the third and fourth experiment, where we added ascorbic acid in the reaction to turn iron 3 ions into iron 2 ions, which thereby reduces the concentration of iron 3 ions. Adding either reactants or products causes a stress. Q value, which shows the result of the equilibrium expression at a stress, will change. If Q changes, the reaction will do the reverse to get back to equilibrium again, so Q is equal to K again. This is called Chatelet's principle. After this stress, the ratio between the reactants and products will be different from before the change, and the equilibrium will counter-react what we do to it. So if we add more reactants, it will reduce reactants to make more products to get a new equilibrium. Therefore, we know that if we make a change in concentration of reactants or products, or change the pressure, Q will change and K will then follow it. If we change the temperature, K changes at first and then Q will follow. We also did a dilution with water, so we added the double amount, where we added water to it, so the volume of the solution were doubled, but the concentration of the molecules were halved. And since these two go out with each other, denominator is multiplied with a half, which is the same as multiplying it with 2, or the double, and therefore the concentrations are decreased, which then results in a shift to a reverse reaction. Thank you for listening. Bye.